Hello everyone, my name is Ashraf Mahgoub. Today I will present Optimus Cloud, Heterogeneous Configuration Optimization for Distributed Databases in the Cloud. This work is a collaboration between Purdue University, Microsoft, Adobe Research, and Google Research, and this project is supported by the NIH. And here is the agenda of our talk today. Now, Optimus Cloud's goal is to achieve cost and performance efficiency for cloud-hosted key-value clusters. And the way Optimus Cloud achieves this goal is through online configuration tuning under dynamic workloads. The configuration parameters that Optimus Cloud considers come from two sets of parameters. The first set is the set of parameters that are exposed by the key-value store itself, such as the size of the cache, the number of reading and writing threads, the compaction method used and the throughput of that compaction method, etc. And the second set of configuration parameters that Optimus Cloud considers is the set of parameters that are controlled by the cloud VM size and type, such as the number of cores, the available memory, and the network bandwidth for every node in the cluster. And under dynamic workloads, by online tuning of these configuration parameters, Optimus Cloud can achieve cost-optimal performance over time. Now let's see why this is a challenging problem. First, to combine these two sets of configuration parameters, the parameters that control the key value store along with the VM type and size, we produce a large configuration space. So for example, Cassandra, which we use in our evaluation, has 25 plus performance tuning parameters. And the Amazon EC2, which we use as our cloud provider, has 133 different instance types and sizes. And those instances vary in price by a factor of 5,000. The second challenge is the dependency between the key value store and the VM configurations. For example, the cache size of Cassandra will be limited by the available RAM in the cloud VM, which is controlled by its type or size. What Optimus Cloud does is it jointly optimizes these two configuration spaces while taking into account the dependencies between them to achieve globally optimized performance. Now, to show how important it is to jointly tune these two spaces, we benchmark one Cassandra server with a 30-minute trace from one of our three workloads, which we will discuss in a few slides, on 6 different EC2 VM types and sizes. For each type and size, we use 300 different database configurations selected through grid search. We show the performance in terms of throughput on the y-axis for the best, the default, and the worst configuration. And we see a big variance in performance with respect to the database configuration, by up to 74% better performance over default configurations. Moreover, the best configurations for every VM type and size is different. Therefore, jointly tuning the configuration parameters of the database with the VM type and size is crucial to achieve optimized performance. And now let's take a quick look at the overview of Optimus Cloud design. The first component in Optimus Cloud is a workload predictor that uses historical traces of the workload, and based on these traces, the workload predictor provides Optimus Cloud with predicted workload patterns for a look-ahead duration. The second component, which is also trained in the offline phase, is a performance prediction model that takes into consideration the workload description, the application configuration, the replication factor consistency level and data placement of the cluster, as well as the VM specs, that is the VM type and size, to predict the performance per dollar for a single server or a complete set. And in the online phase, the third component, which is the cluster performance predictor, takes the predicted values of the performance for every server, as well as the predicted workload and the information of the cluster, such as the replication factor and the consistency level, to predict what would be the total operations per second on the cluster level. The fourth component takes this total ops per second for the cluster level and performs the optimization given the user's budget and the minimum ops per second, as well as the cloud provider cost model to find the optimal cloud configurations as well as key value store configurations for our cluster. Under dynamic workloads, which we often see in practice, the workload characteristics change very frequently over time, sometimes in an unpredictable way. And this makes the problem even more challenging because upon a workload change, my old configurations might not be optimized for the new workload, and therefore a reconfiguration is necessary. However, doing this reconfiguration in runtime usually requires a server restart, and that causes a downtime and a degradation in performance. So for fast-changing workloads, these frequent reconfiguration will add these transient downtime and degradation in performance, which can cause severe degradation of the overall cluster performance over time. And the question that Optimus Cloud is trying to answer is, can we reconfigure only a subset of the nodes in the cluster to achieve globally optimized performance while minimizing the downgrade time due to reconfiguration? And if so, which nodes should we reconfigure upon a workload change? And also notice that changing the configurations of only a subset of the nodes will lead to heterogeneous configurations, and that is by itself a new challenge. Here we show an example of why heterogeneous configurations are beneficial. We benchmark a cluster of 4 Cassandra nodes with our MG Rust workload, and that workload switches between read-heavy phases and write-heavy phases. And for this benchmark, we use all combinations of 2 VM instance types and size, C4.large and R4.xlarge. We noticed the following. With all nodes configured to C4.large, we achieve the best write performance. However, we also achieve the lowest read performance because C4.large has very small RAM. Now, by reconfiguring 2 of the nodes to R4.xlarge, which has much bigger RAM size than C4, we notice that there is a degradation in performance with respect to writes. However, we see a 9x improvement with respect to reads. We also notice that changing more nodes to R4.xlarge reduces the performance for both reads and writes. Accordingly, the best configurations is to use all C4.large for write-heavy phases of the workload, while reconfiguring only 2 servers to R4.xlarge when the workload becomes read-heavy. So heterogeneous configurations have the advantage of reducing the reconfiguration downtime, along with avoiding over-provisioning by reconfiguring the minimum number of nodes needed to achieve the best performance. However, this comes with a new challenge, which is the additional increase in the search space due to heterogeneity. Consider a cluster of 20 nodes and 15 different configurations to pick from. If we only consider homogeneous configurations, then we have 15 options no matter what the cluster size is. However, with heterogeneous configurations, the problem becomes similar to distributing 20 identical balls over 15 boxes, causing the number of possible configurations to be 1.3 multiplied by 10 to the power of 9 possible configurations, and this is indeed infeasible to model or optimize. And to solve this problem, Optimus Cloud introduces the concept of complete sets, which we define as the minimum subset of nodes for which the union of their data records covers all the records in the database at least once. So this concept of complete sets relies on selecting the fastest replica for a given request, which is implemented in many key value stores. For example, this is achieved through a dynamic snitch of Cassandra or the adaptive replica selection in Elasticsearch. And given that using the concept of a consistency level, we can define how many replicas need to reply to a request before it is satisfied and returned to the user. And therefore, the latency of the request is dominated by the slowest replica. And the servers within a complete set must be upgraded to the faster configuration upon a workload change for the cluster performance to improve. Accordingly, Optimus Cloud keeps the configurations to be homogeneous within the same complete set, while allowing different complete sets to have different configurations. And now we show how partitioning the cluster into complete sets reduces the search space. First, we show that the number of complete sets in any cluster is upper bounded by the replication factor. For the details of the proof, please see our paper. And also knowing that the replication factor is practically low, with 3 or 5 being a practical upper bound, along with reconfiguring a number of complete sets that is equivalent to the consistency level, we guarantee that all requests are served from nodes with optimized configurations. And revisiting the same example with 20 nodes and 15 configuration parameters to select from, now with partitioning the cluster into S complete sets, we have only 680 possible configurations compared to 1.3 multiplied by 10 to the power of 9 if we don't partition the cluster into complete sets. And this space of 680 possible configurations is indeed feasible to model and optimize. Now, this is an example of how Optimus Cloud identifies complete sets in the cluster using the data placement information for every node. The first cluster on the left-hand side, cluster 1, has a complete set configured to R4. And R4 is memory optimized and therefore achieves 7x better reads per second compared to cluster 2. Notice that cluster 2 is using the exact same resources as cluster 1, however, it doesn't take into consideration the data placement information for every node and therefore doesn't configure a complete set to the read optimized configuration, causing its read performance to be very low. And before we go to our evaluation, we'll first introduce the 3 applications that we use as our benchmarking workload. The first application is the largest metagenomics analysis portal called MGRest, and for which we use the real workload trace to replay, and we see that there is no daily or weekly pattern in the workload, and the workload changes very drastically over time, which makes it very hard to predict a look-ahead period more than 5 minutes. The second application is a real trace from a bus tracking mobile application, and for that particular application, we see that there is a strong daily and weekly pattern in the workload switches. And this causes a much longer and more accurate look-ahead period of 1 hour or 2 hours. And the third application is a simulated workload trace from batch data analytics jobs. And using priorly introduced profiling techniques, the job execution times and resource allocation are predictable for a longer look-ahead period. Here we show the performance prediction accuracy of Optimus Cloud in terms of R-square and root mean square error. We compare to several baselines. The first baseline, that we call N solitary models, builds a performance prediction model for every VM type or size. Selecta uses a singular value decomposition based technique to infer the performance for unseen configurations. And Optimus Cloud compares 2 approaches. one that describes the VM type or size as a categorical parameter versus a second that describes the VM type or size in terms of its number of cores, amount of memory, and network bandwidth, which we call Optimus numerical. This numerical model achieves better performance than all other baselines due to its ability to perform transfer learning between different VM types and sizes. We also introduce the 4 baselines that we compare the performance of Optimus Cloud to. The first baseline is a homogeneous static configuration that is optimized for the entire duration of the predicted workload, but it is a static configuration that the same configuration is being used for the entire duration of the benchmark. The second technique is a reactive technique called CherryPick, which was introduced in NSDI 17. CherryPick uses Bayesian optimization to find a heterogeneous cloud configuration for a representative job or phase of the workload. The third baseline is Selecta, which was introduced in USENIX ATC 18. Selecta uses a singular value decomposition technique to select the optimized homogeneous cloud configuration for different jobs or phases of the workload, which is also a reactive technique. And the fourth baseline is our paper from ATC 19, Sophia, in which we used genetic algorithms and performance modeling to find optimized homogeneous configurations, which only considers the key value store parameters without configuring the cloud in an online manner. Here we show the performance of Optimus Cloud compared to the 4 baselines that we just introduced in terms of throughput per dollar, as well as the tail latency or the P99 latency. In all 3 applications, Optimus Cloud achieves the best throughput per dollar or ops per second per dollar without sacrificing or increasing the tail latency. Optimus Cloud achieves up to 86% better performance per dollar over the homogeneous static configuration due to Optimus Cloud's capability of performing online reconfiguration. Also, Optimus Cloud achieves up to 173% and 130% over both CherryPick and Selecta respectively due to its ability to reconfigure only a subset of the nodes, which minimizes the reconfiguration downtime and avoids over-provisioning. Compared to Sophia, Optimus Cloud achieves up to 212% better performance per dollar, as Sophia considers only homogeneous configurations, also for only the key value store parameters. These observations together show the importance of our 2 main contributions. First, we jointly tune key value store parameters with cloud VM parameters, and we perform heterogeneous configurations to achieve globally optimized performance over time. Now, since Optimus Cloud relies on 2 types of predictors, the workload predictor as well as the performance predictor, we want to investigate how tolerant Optimus Cloud is to errors in both predictors. Therefore, in this experiment, we add synthetic noise to the output of each predictor separately, and then show how does the benefit of Optimus Cloud change with the amount of synthetic noise. We draw the noise on the x-axis and the improvement over homogeneous static on the y-axis. The percentage of noise is represented as a uniform random variable that is added or subtracted from the output of the predictor. As expected, the performance of Optimus Cloud over homogeneous static decreases with increasing levels of noise, as the selected configurations deviate from the best configurations. We also notice that Optimus Cloud is more sensitive to errors in the throughput predictor compared to the errors in the workload predictor, which is demonstrated in the steeper downward slope in the noisy throughput predictor curve. The reason is that a slight deviation from the optimal configurations that is proposed by the performance predictor causes a significant reduction in performance per dollar. On the other hand, slight errors in workload predictor causes Optimus Cloud to reconfigure either earlier or later than it optimally should, but still achieves the gain of the overlapped duration between the actual and the predicted workloads. To conclude our talk, we find that for cost-optimal performance of a distributed key-value store cluster in the cloud, it is critical to jointly tune both the key-value store configuration parameters along with the cloud VM configuration parameters to achieve cost-optimized performance. Optimus Cloud provides the insight that it is optimal to create heterogeneous configurations, and for this, it determines at runtime the minimum number of servers to reconfigure. This, of course, reduces the reconfiguration downtime and avoids over-provisioning, but also increases the search space. And using a novel concept of complete sets, Optimus Cloud provides a technique to search through this large space that is brought by heterogeneity. Configurations found by Optimus Cloud outperform those by prior works CherryPick, Selecta, and Sophia in both performance per dollar or throughput per dollar and tail latency. And here we reach the end of our talk, and I will be happy to take any questions. Thank you.